an isosceles prism kept at a position of minimum deviation. Let there be an isosceles prism where a monochromatic light falls at the point B. If you draw normal at the point B, we can get angle of incidence I and angle of refraction R1. BC is the refracted ray. At the point C, we can draw a normal N2 so that we can get angle of refraction R2 and angle of emergence E. Delta is the angle of deviation and A is the angle of prism. Now when this prism is kept at such a position so that the deviation produced by the prism is minimum, we have two important conditions which are true. First, the two angle of refractions are equal. Angle R1 is equal to angle R2. And second, the angle of incidence is equal to angle of emergence. That is, angle I is equal to angle E. When these two conditions are true for an isosceles prism, the refracted ray BC will be always parallel to the base of the prism. When an isosceles prism is kept at a position of minimum deviation, we can calculate the expression for angle of refraction R. The angle of refraction R1 and R2 are both equal, they are equal to R. We have got one simple formula, A is equal to R1 plus R2. R1 and R2 are equal, A will become equal to 2R, and R in this case will be A upon 2. That is angle of refraction, whether it is R1 or it is R2, they both are equal, they are equal to half the angle of prism. Expression for the angle of incidence when the prism is kept at a position of minimum deviation. There is an isosceles prism where a monochromatic light falls at the point B. When you draw normal at the point B and 1, we can get angle of incidence I and angle of refraction R1. At the point B, the light is going from air to glass. If you apply Snell's law at the point B, we will be getting refractive index of air into sine I is equal to refractive index of glass into sine R1. R1 and R2 are equal, they both are equal to A upon 2 and the refractive index of air is equal to 1. If you substitute these values in this formula, we will be getting sine I is equal to refractive index of glass into sine A upon 2. Therefore, I will become sine inverse refractive index of glass into sine A upon 2. I and E are both equal, they are equal to this value. We can calculate the angle of minimum deviation when the prism is kept at a position of minimum deviation. We have got one simple formula, A plus delta is equal to I plus E. I and E are equal if angle of deviation is minimum. We can put A plus delta M, which is the angle of minimum deviation, is equal to I plus I, that is 2I. So delta M, if you take A on the other side, delta M will become 2I minus A. And I is sine inverse refractive index of glass into sine A upon 2. Therefore, we will be getting delta M, angle of minimum deviation, is equal to 2 times sine inverse refractive index of glass into sine A upon 2 minus A. We can calculate the refractive index of the material of the glass when the prism is kept at a position of minimum deviation. Let there be an isosceles prism kept at a position of minimum deviation. There is a monochromatic light falls on the prism at the point B. N1 is the normal drawn at the point B. I is the angle of incidence and R1 is the angle of refraction. At the point B, light is going from air to glass. We can calculate individual angles at the point B. Expression for the I can be calculated by using one formula, I plus E is equal to A plus delta. I and E are equal when delta is equal to delta M, angle of minimum deviation. That means 2I will become A plus delta M, I will become A plus delta M upon 2. We can calculate the angle of refraction R again by using the formula R1 plus R2 is equal to A. At the position of minimum deviation, R1 and R2 are equal. Therefore, 2r will become equal to a, r will become equal to a upon 2. We can apply Snell's law at the point B. Refractive index of glass into sine R1 is equal to refractive index of air into sine I. We can put the value for R1 as a upon 2 and I as a plus delta m upon 2, so that we can get the refractive index of glass as sine a plus delta m upon 2 upon sine a upon 2.